Up next, I want to look at this matrix and these two vectors. So A is the matrix 3, -2, 1, 0. U is the vector -1, 1, and V is the vector 2, 1. And I want to find AU and AV. So notice that we're going to be multiplying a couple of different vectors by A. So it might be useful to have our calculator know what the matrix A is. So if we go into if we're going to use a matrix over and over again, if we go into matrix and then go over to edit, we can edit matrix A. We can enter the size of the matrix, in case it's 2 by 2. And I want 3, -2, 1, 0. I'm just hitting enter in between each one. Now my calculator has a button that will bring up this matrix, 3, -2, 1, 0. So from the home screen, I could, if I go to matrix names and hit A, that will display the matrix A. And I could use this matrix A in operations. So for example, if I wanted to find the reduced row echelon form of the matrix A, I can get the reduced row echelon form of A. And so we see that A is invertible because it's row equivalent to the identity matrix. That means 3, 1, -2, 0, 3, 1, and -2, 0 form a basis for R2 because it's a linearly independent spanning set for R2. But what I want to do is multiply A times the vector -1, 1. So I'm going to go to matrix, and I'm going to multiply by -1, 1. So when I make a matrix, I put brackets around the matrix and brackets around each row. So that means I need like excessive amounts of brackets for to write a column vector, but that's okay. So AU is equal to -5, -1. Now, if I want to do AV, I'm just going to edit my previous one. So I press second enter, and that'll bring up what I just did. And I'm going to change the -1 to a 2. I'll get rid of the negative and put 2. And so A times 2, 1 is 4, 2. So it's not obvious right now, just doing these multiplications, that something interesting has happened, but something interesting has happened. If I look at what A did to the vector U, I went from -1, 1 to -5, -1. So U is going in this direction, -1, 1. But AU is going the direction -5, -1. So multiplying by A stretched the vector U, it's longer, and it also rotated it through some angle. We can calculate the angle, we don't need it right now. But look at what happened when we multiply A times V. I have the vector V, which is 2, 1, so 2, 1. There's the vector V. And the vector AV is just 2 times the vector V. We're going in the same direction. Multiplying by A did not change the direction of the vector V. It just made it longer. So multiplying A by U changed the magnitude and the direction, but multiplying A times V only changed the magnitude. It just stretched the vector V. So multiplying by A change magnitude and direction. But in AV, it only changed magnitude and direction of U. But when I multiplied by V, we only changed the magnitude, did not change the direction. Moreover, anything in the direction of 2, 1 will always maintain that direction if I multiply by A. If I multiply A, let's change our 2, 1. Let's multiply A by something else in that direction. Let's do A. I'm going to write it out. I didn't want to write it out. Why did I do that? That seems strange. I'm going to multiply A by, instead of 2, 1, I'm going to multiply it by 20 and 10. Before we hit enter on the calculator, take a guess at what's going to happen. What's going to happen if I multiply A by 20, 10? $40.20, that's a good guess. Let's see what happens. $40.20. Notice that $40.20 is in the same direction as V. What if we go in a different direction? What if I do A times -2, -1? What are we going to get? -4, -2. Pretty good guess. So the interesting thing that happens here, now the scaling business is not that interesting because matrix multiplication is a linear transformation, and linear transformations respect linear combinations. The interesting thing is that the output is in the same direction as the input. So in this case, A times the vector V is just a scalar multiple times V. That's the interesting thing. A times V is just a scalar multiple of 2, and specifically always 2 times what we started with. Multiplying anything in the direction of 2, 1 by the matrix A just multiplies by 2. That did not happen with the vector U. Multiplying A by the vector -1, 1 changed the magnitude and the direction. It's AU is not just a scalar times U. So right now, for some reason, I'm calling out this as being important. But I haven't said why, for reasons. But that's what we're calling out. It is interesting when this happens. When we multiply a particular vector, a matrix by a particular vector, we just get a scalar multiple of what we started with. There's another vector that does this for the matrix A. So if I take the matrix A, I'm going to call the vector W. I'm just going to write the matrix A. If I take the matrix 3, 1, negative 2, 0, and multiply it by 1, 1, I just get back what we started with, 1, 1. So if I multiply this by 5, 5, I get back 5, 5. So if I didn't want to name this as vector W. So A times W is just 1 times W. It's interesting that multiplication of these particular vectors by this matrix results in just a scalar multiple of our vector. It's interesting that multiplication of these vectors by this matrix results in scaling, not a change in direction.
I have a question.
Uh-huh.
Every time you just change the first row, what happens if we change the second row?
If I change what?
The second row for W or U, where the V was 2, 1, and for W is 1, 1.
Uh-huh.
So what happens if you change 1 to something else?
Then we will not get, if I change, say, if instead of doing 1, 1 or 2, 1, if I do 3, 1, then that doesn't happen. I've changed the direction and I've changed the magnitude. So 3, 1 is not interesting to matrix A. It's interesting when I multiply this matrix by these vectors, and it results in just a scalar multiple of the vectors. This matrix A, by these vectors, it was U and W. And it just results in a scalar multiple of these vectors. There is a special relationship between this matrix and these two vectors and the scalars 2 and 1 that go with each of these vectors. So one of the reasons that this is useful is that matrix multiplication could represent some kind of change in conditions. So the leading example here was using a matrix to model how the spotted owl population changes. So what we're looking for is multiplication of our vectors for a matrix such that when we multiply the matrix by the vector, we just get a scalar multiple of the vector we started with. This is interesting because if multiplication by this matrix represents some kind of change, so from year to year, let's say, every year we multiply by this matrix to find the new conditions. Multiplying by A, multiplying these vectors by A is really straightforward. Because if I multiply A times the vector 2, 1, oops. Now it worked. And if I multiply again by A, I'm going to go from 4, since 4, 2 is on the same line as A, I'm just going to go further. I'm going to multiply by 2 again. So A times, let's go to entry, and then just insert another A. So if I multiply by A again, this particular vector, I'm just going to keep getting a longer vector. So if I insert another times A, I'm just going to multiply by the previous vector by 2 again. Now this doesn't happen if I start with a vector that's not 2, 1 or 1, 1. So if I go to the vector 3, 1, I'm not going to be on the same line because 3, 1 and the matrix A do not have this interesting relationship. So this is our next big thing. I didn't put a title up here, but here's our next big thing. So this matrix A has these two eigenvectors. We would say that 2, 1 is an eigenvector of A corresponding to eigenvalue 2. And we would say that 1, 1 is an eigenvector of A corresponding to the eigenvalue 1. Eigenvectors are interesting because multiplication by the matrix of a matrix are interesting because multiplication by that matrix only results in a stretch. If the eigenvalue is less than 1, it's a reciprocal stretch or a squish. Squish is not the technical term. I just can't remember what the opposite of dilates is. Undilates? Shrinks? Contraction? That's probably if we want to sound fancy. But when we're just talking, I always just say squish. Thank you. Contract is probably a better word. Like if you had a professional teacher, they'd use fancy words. But unfortunately for y'all, you're stuck with me. So I'm like, all stretch, squish. I do the same thing when you're talking about graphs and you do multiplication of your inputs or before your function or after your function, where you stretch or squish horizontally or vertically. I should write a math book specifically to find out if the editor would let me use the word squish. All right, so that's going to be our next big thing. What you need to work on this weekend is this weekend and next week, work on test 2. My job is this week, the rest of this week and this weekend to grade all the quizzes from chapter 2. There are like 4 quizzes on matrix operations and matrix inverses. So I'll get scoring on those. Do your resubmissions for test 1. Do your first submission for test 2. Your homework job this week is to work on chapter 4 and begin chapter 5. And then start working on the quizzes for chapter 4. It only sounds like you have a lot to do because you have a lot to do. But we're coming up on the end. After today, there's only 4 more class meetings. There's only 2 more weeks. And we know pretty much all the things that we need to know. We just need to take what we know and add to it. Expand on the things that we already know. Because it's all just linear combinations. All right, that's going to do it for today. That's going to do it for this week. Everybody have a good weekend, and I'll see you all on Monday. And thanks for playing.